Today we will discuss heat and temperature and all things related. First of all, temperature itself is the measurement of the energy within something, specifically the kinetic energy or the way or the speed in which the particles are moving. It's like a measurement of the thermal energy that a particle or a substance has. So we've talked about things like this before. Here on the left, these gas particles are moving clearly more slowly than these gas particles on the right, meaning obviously the temperature of these gas particles on the left is going to be lower than the temperature of the particles on the right because we're measuring once again the motion of those particles. These are moving much more quickly, therefore they have more kinetic energy, therefore the temperature will be higher. So if temperature is the measurement of the thermal energy, or the measurement of the motion of the particles, heat is the transfer of that thermal energy between two objects. We, in regular everyday speak, talk about heat as being whether something's hot or cold, but it's actually hot and cold are the feelings that you get when heat is taking place. Heat is the transfer of that energy. And energy is always transferred from the object with the higher temperature or the higher level of motion to that of something with a lower temperature or a lower relative motion, because nature wants to be in equilibrium. So if it's higher temperature, it's going to transfer thermal energy to a lower temperature, which is going to be heat, transferring from higher temperature to lower temperature. So when you actually feel cold, what you feel is the thermal energy leaving you and spreading to the area around you, which is clearly at a lower temperature, and it's your body is transferring some of that heat. Nature wants to be in equilibrium, so you're losing some thermal energy to the air around you. So when it's colder outside, you feel cold, but what you're actually feeling is thermal energy transferring from your body to the air around you. So it happens in multiple ways, this transfer of thermal energy. One of those ways is conduction. Okay, this is the transfer of thermal energy through direct contact. So if this griddle here that's on the stove is full of thermal energy. The temperature's high, the particles are moving very quickly, it's full of thermal energy. These pancakes and this sausage, they, however, have a lower level of thermal energy, and as they come into direct contact with the heating plate here, the heating plate transfers thermal energy to this food, thereby raising its temperature and cooking it. But it's transferred through direct contact. When they touch the griddle, they get some of that thermal energy transfer. They get that heat. So conduction is a way to transfer thermal energy. Conduction is a method of heat transfer. So things like metals are good conductors because they transfer this thermal energy well. We want our cooking utensils to be metal, so they transfer that thermal energy well so that it's efficient when things are cooked. Insulators, such as this can koozie, do not transfer energy well, which is great because we don't want this can to absorb any energy from the air around it. You want our can to be cold, so we don't want it to absorb any of that energy, so we place this insulator in between it and the air around it and between it and our hands because it does not transfer that energy well, and we don't want it to absorb any of that energy, so that's perfect. So some things that are good conductors, as you can see, all metals, right? Curling iron, made of metal. Iron skillet, made of metal. Cookie sheets, they're made of metal. Copper pipes are made of metal. And the coils on your stove that transfer, on some people's stoves, that transfer the electrical energy and turn it into that thermal energy, they're metal because we want that to transfer energy well. Things that we don't want to transfer well, things that we want to insulate us, such as our clothes, a flannel shirt. We want it to insulate us in the winter, keep us from transferring some of our thermal energy to the cold air around us. An oven mitt, you obviously don't want the pot or pan from your stove or oven to transfer its thermal energy to you, so you place an insulator, an oven mitt, in between you and the oven or stove or pot or pan. All right, radiation is another way to transfer thermal energy. It happens through the air, transfers heat or thermal energy through the air. That's how the sun's energy gets to us. In your toaster, the bread does not touch directly the heating coils. Then you would have a little pattern on your bread. It does not. The heat from the heating coils, the thermal energy, is transferred through the air to your bread, turning it into toast. And here we are harvesting some of that solar energy in some solar panels. Once again, that solar energy traveling through the air, it is radiation, transfer of energy through the air. And convection. This is the transfer of energy by the movement of liquids or gases. Here on our stove, we have our pot, we have our burner, this is our flame. It is directly touching the pot, transferring thermal energy through conduction. And where the pot is directly contacting the water, it is also transferring by conduction. But when the particles heat up of the water here, they move faster and become less dense. We know that things that are less dense rise above things that are more dense, so the cooler liquid falls because it's more dense now than the liquid that has been heated. And then when the liquid gets up here, it begins to cool off slightly as this liquid down here is heating up again, and it basically creates a circle. This is called a convection current, and it continues like this until all of the liquid is of the same temperature. It is heating it by the movement of this liquid. The same thing happens for the air in our atmosphere. The sun radiates its energy to the earth. The earth's surface absorbs that energy through radiation and then transfers that energy to the air directly in contact with it through conduction. And then that air, once again, as it heats up, it becomes less dense and it rises. And the cooler air that is more dense falls, and it creates that convection current again, only this time it's a gas instead of the liquid. So convection can happen in liquids or in gases. Thermal expansion is something that can happen when the temperature of something increases, right? The particles are moving faster as the temperature increases, and so they take up slightly more space. So thermal expansion is something that happens when materials absorb thermal energy, thereby raising their temperature and having their particles move more quickly and take up a little bit more space because they're moving around more. This is a snapshot of a bridge, and this is a metal plate on that bridge. It's called a thermal expansion plate. As the concrete of the bridge absorbs solar energy and gets a higher temperature, that bridge will expand a little bit. This plate here allows for it to expand some during the day and not, run into itself and crumble. And then it allows for it to contract a little bit at night when the temperature goes down and those particles slow down and it takes up slightly less space. It allows it to do that and not fall apart. This is a thermometer. It is based on the idea of thermal expansion. As the liquid absorbs more thermal energy, the temperature rises of that liquid, causing it to take up slightly more space, and it goes up this very thin tube in the center of the thermometer. As it expands, it goes up. It's a very thin tube, and it is relative to the temperature of the liquid. So let's talk about how much heat something has. Okay, if we got temperature, that's the measure of a substance's kinetic energy. We have heat is the transfer of that energy, but how can we measure how much energy is being transferred? We can do that by having the knowledge of some specific properties of matter that we know, and those can help us to determine how much heat is being transferred and how much of a change in temperature we will get from a heat transfer. So one of those things is heat capacity. Okay, heat capacity is something that relates the amount of energy absorbed by a substance to its corresponding rise in temperature. So it tells us, oh, if this is absorbing this much energy and it raises the temperature by this much, then we know about how much energy it takes to raise the temperature of that object. Okay, we have the amount of energy, and you divide that by the amount of the temperature raise. So, for an example, if it takes 2,093 joules, remember we talked about joules of energy, which is also 293 joules is the same as 500 calories of energy. Calories is obviously food energy. To raise the temperature of a glass of milk, so 2,093 joules or 500 calories to raise the temperature of a glass of milk by 10 degrees, and then we just divide that out, right? 2,093, that's the amount of energy. Divide that by the change in temperature, which is 10 degrees, and that tells us that 209.3 joules is what it takes to raise that amount of milk by each degree Celsius. That is called heat capacity. So it's the amount of heat it takes to raise a certain amount of liquid or a substance by a certain amount of degrees. And we obviously measure degrees in Celsius in the metric system. Something even better is a specific heat capacity. We refer to this as the specific heat of an object. Okay, that's a physical property of matter. It does not change for each kind of matter. Specific heat tells us how much energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. This is, once again, it's a physical property. It does not change. It's basically kind of telling us how something absorbs energy, or how well or how quickly it absorbs energy. Specific heat allows us to determine how fast an object is going to heat up, and if we have a bunch of substances, we can tell which one is going to heat up faster, which one's going to absorb that heat more efficiently. Specific heat tells us that. It tells us how fast something absorbs energy. We generally measure this. The energy that we're talking about, once again, is generally measured in joules and calories. And specific heat, once again, does not change for specific substances. Here are some examples. Regular liquid water. Okay, it takes 4.18 joules to raise the temperature of 1 gram of water by 1 degree Celsius. Regular air around us, dry air around us. It takes 1 joule of energy to raise regular dry air by 1 degree Celsius, 1 gram of dry air by 1 degree Celsius. And you can see that water has a very high specific heat. It's not very efficient at absorbing energy because it takes a lot more energy to raise the temperature of liquid water than it does to raise the temperature of lead or copper or iron, which would mean liquid water would actually be a pretty good insulator, compared, of course, to these metals, which transfer or absorb that energy very quickly. This is the formula that we will be working with that helps us to examine the relationship between the amount of heat we add to the specific heat of the substance, the mass of that substance, and the change in temperature. This triangle here is used in science to take the place of the words change in. So we're talking relating the heat to the specific heat of a substance, the mass of that substance that we have, and whatever the change in temperature is. The formula is very important because it lets us work with all of these things, and it helps us to find out things that we don't know by substituting in the things that we do know. Okay, once we plug in the information that we have, we are allowed then to mathematically determine the information that we want to know. As long as we have 3 of these total 4 parts, if we have 3 of them, we can find whatever that 4th part is. Okay, this formula allows us to determine how much heat has been added to a substance if we know that substance's specific heat, we know that substance's mass, and we know how much the temperature changed. So we'd be able to determine how much heat has been added. We can determine how much the temperature is going to change if we add a specific amount of heat, as long as we know the specific heat of the substance and the mass of that substance we have. And we can tell what the specific heat of a substance is if we know how much heat we're adding, the mass of the substance, and how much the temperature change. So we can determine all these things by having 3 out of 4 of these parts.